Hello guys, good morning. For the consolidation chapter, at least you have to know how to use three diagrams. The first diagram is the pressure and the void ratio diagrams. This diagram you can use to calculate the pre-consolidation pressure and the compression index. The first thing you have to know how to read the diagram. The x-axis is for the log scale of the pressure and the y-axis is the void ratio. The upper part of the curve is the low pressure part, or you can say is the recompression, and the lower part is the high pressure part or virgin compression line. Okay, let's start with finding the pre-consolidation pressure. The first step is you have to plot the point of the maximum curvature on the curve. I think for this case, the maximum point is on the third point from the left, and this point it becomes the reference point for the tangent line, horizontal line, and the angle of the bisector. Okay, next step you have to make a tangent line at the maximum curvature point like this. This line follows the local direction of the compression curves. Okay, next step you have to draw a horizontal line through the same point. Okay, like this one. Okay, next you have to divide the angle between those lines into two equal parts, so the bisector will intersect the virgin compression line. Next, you can draw a straight line from the high pressure line through upward until meets the angle of the bisector. You will get the intersection between those points. That intersection is the pre-consolidation pressure. How to know the pre-consolidation? You have to draw the straight vertical line to the x-axis, and that point is the value of the pre-consolidation pressure. In this case is equal to 70 kilopascal for the pre-consolidation pressure. Okay, next we can calculate the compression index. This is the formula for the compression index is the initial void ratio minus final void ratio divided by log of final pressure minus by log initial pressure. To get the value for the initial and the final point, you can pick two random points from the high pressure line, so you will get the coordinate for each points. You can simplify the formula into initial void ratio minus by final void ratio divided by log final pressure divided by initial pressure. Next, you can use directly the formula with the value of the coordinates from each points. Okay, 1.39 minus 1.25 divided by log 480 divided by 250, so you will get the value for the compression index equal to 0.49. Okay, next to the second diagram. This is the second diagram. This diagram you can use to calculate the time of consolidation and the coefficient of consolidations. There's two major methods to calculate the time and the coefficient of consolidations. The first is Casagrande methods, and the second one is the Taylor methods. What's the differences between those methods? The Casagrande methods use log times as an x-axis, and the Casagrande methods use root times for the x-axis. Okay, first we try to calculate the time and the coefficient with the Casagrande. Before we start drawing, I think we have to know the symbols or the symbology for the parameters. The first is R. R stands for the dial reading of the settlement. And you have to know U. U is the degree of the consolidations. And there's T50 and T90. That is the time required for the soil specimen to reach the percentage of primary consolidations. The T50 is time required to reach 50% of primary consolidations, and T90 is time required to reach 90% of primary consolidations. Okay. And there's another T. There's T50, another T50 and T90. This is the time factor or theoretical time factor for the calculations. I think from the Terzaghi theory, T50 value is 0.197, and for the T90 is 0.848. Okay. Next is HDR. HDR is the drainage path length. For the double drainage, you can use H divided by 2, and for the single drainage, you can use H. Okay, next is CV. CV is the coefficient of consolidations. Okay, next we start for the drawings. First step, you can draw the straight line from the secondary consolidations and primary consolidation curves until you get the intersections between those lines. The intersections of those lines, it's the R100 or the 100% of primary consolidations. And if you draw the straight lines into x-axis, you can get the time for the R100. Okay. The value of R100, it's equal to 0.7, and the T100, you can how much? Okay. You can take the value equal to 90 seconds, and this is millimeter. Okay, next you can choose 2 points for points A and point B as the point A is the T1 and the point B is 4 times of T1. That's 4 point B. Need T1, it's T2. T2 is equal 4 by T1. Okay. And then next, you can draw the horizontal line above the point A and point B. So we can get the difference between the point A and point B. And you can move the same distance from T1 line to define the R0, same length. Okay. Those line, it's the lines that we need to draw to define the R0. Okay. Okay. So now we can get the first line as an R0 and the second line as an R100, R100. So if we divide by 2 for the length of distance from the lines, you can get the value of the R50. Okay. So we can get the point of or the value of time 50. The time required to the soil specimen reach the 50% of the consolidations. The value of T50 equal to 30 seconds. Okay. And then we can go to calculate the coefficient consolidation for 50%. The formula for the coefficient consolidation is CV equal to T50 multiplied by HDR square divide by T50. Okay, assume the HDR equal to 3 meters. So we can calculate the CV equal to T50 equal to 0.197. So 0.197 multiplied by 3. We have to convert this to millimeters. So there's equal to 3000 millimeters divided by 3000 square divided by 30. So after we calculate it, we can get the value for the CV with the Casagrande methods. Next methods is the Taylor methods. Okay, for the Taylor methods, first step you have to make a straight line from the curve to the y-axis, like this. Okay. So we can get the point of A. After that, the second step, you have to calculate the point B. The point B is the A by 1.15, 1.15. So assume the point B at this point B. So we have to draw the straight line from the point B into the y-axis of the point A. After that, we can get the intersection between the line B with the curve. The intersection between those lines is the R90. So we can get the T90, or the time required to the soil specimen to reach the 90% of primary consolidations. Oh, sorry, this is the R0. Okay, next, I think we can directly calculate the coefficient of the consolidations for 90%. And the formula, it seems, with the CV for 50%, but we have to use the time factor of 90. HDR square divided by T90. Assume the HDR is equal to 3 meters or 3000 millimeters. So we can get the coefficients of consolidations equal to, as I said before, the T90 is 0.848. 0.4 times 3000 square. Since the T90 is in the root form, so we have to calculate the T90. T90 is root by 2. So we can write it. After we calculate the formula with the value for each parameters, we can get the coefficients of 90% consolidations with the Taylor methods. Okay, next, I think I have to explain you what the difference between single drainage and double drainage. For determine the length of drainage path or HDR to calculate the coefficient consolidations. Okay. The difference between single and the double, it's the soil that being analyzed. For the single drainage conditions, it's on impervious layer. And for the double drainage conditions, the soil that being analyzed is bounded by two pervious layer. Usually the layer it's sand. For the single drainage, you can use H for the value of HDR. For the double drainage condition, you have to divide the H by 2 for determine the HDR value. For simplified, the single drainage is on impervious layer, And for the double drainage, it's bounded by two perfuse sand layer. Okay, thank you.